We've all been here. We found the perfect image for a presentation, but it's just too small to scale to our project, resulting in disgustingly blurred outlines. We've wondered why. Oh, why can I not smoothly upscale this image? Well, fear or not, because, at least for easily traceable images, Bezier curves and B-Splines come to the rescue. Whip out your favorite image manipulation program, I'm using GIMP here, and follow along. First, you want to upscale your image to the dimensions you want it to be in. Then, find your path tool and place points along the edges you want to trace in the following manner. No curve between the point? Good, don't worry about it. Just put the points on the ends of the line you're tracing. Curve between the points? Place a point wherever the incline of the line changes from positive to negative or vice versa respective to your last point placed. It's kind of a feeling thing. Roughly like this. Now, depending on your software, use the path tool to drag out a curve between the points, fine-tuning with the respective control points, and repeat all around the edges of the image. Now, what we've created is a path around the image that is not statically defined by pixels placed, but by mathematical equations, so it is infinitely scalable, because the data is practically analog instead of digital. Filling the path will convert it back to digital data, because your program is going to place pixels, but now all your borders are nicely scaled up. Great job! So, why am I showing you this? This is neuroinformatics, right? Well, because I had to do it for a job for a while, and honestly I just want others to suffer along with me, but more importantly, it dynamically shows you how Bezier curves and B-Splines work. A Bezier curve is essentially a smooth curve defined by 4 control points and some math. B-Splines, also known as basis splines, are essentially concatenated Bezier curves. Here's how it works. This is the Busy Bee Curves app. If you want to play around with it, the link is on screen. It's a tool that helps you understand Bezier curves and B-Splines. The blue nodes are the control points I've talked about earlier. We can move them around all the while tracing in real time how our curve is gonna look. Now, watch what happens when I click Start Animation. The thick red line is our Bezier curve, and mathematically it's just a polynomial. Put formally, a Bezier curve is a parametric curve C of t equal to the pair of x of t and y of t, where x of t and y of t are each real-valued polynomials. The unique thing about Bezier curves is that they're determined by the 4 control points, which are shaded in blue. These points belong to their own functions themselves, which are displayed in green right next to the control points. They're called Bernstein basis polynomials. The size of the blue circles is determined by the respective value of the graph, and changes as our Bezier curve moves along the thick red line. At all points, the parameters of the blue circles add up to 1. By changing the control points, we change the shape of the Bezier curve. The yellow circle on our Bezier curve is always at the center of mass of the blue control points, where the mass of each control point is equal to the area of the blue circle. The number next to this yellow circle, the parameter, varies between 0 and 1. Alright, so much for the nice illustration, but let's cut down to the chase. How do Bezier curves look when we express them in mathematical formulas? This is how the most basic form of a Bezier looks as a formula. The p's indicate the position of the control points. The parameter t can be seen as the running variable. It draws the curve by increasing from 0 to 1. Okay, so how does this equation work? To begin with, let's set t to 0. As we can see, the brackets disappear, and all that's left is the control point p0. And that makes total sense, as we are at t0 in our Bezier curve, which is nothing but our first control point. Now, what happens when t increases? The influence of p0 decreases, while the influence of p1 and p2 increases, until up to a certain point, the influence of p1 also starts to decrease more than it increases. This dynamic procedure is the secret behind Bezier curves, and that is only the beginning. As we already mentioned in the beginning, we can paste lots and lots of Bezier curves together in some form of end-to-end conjunction. Let's look at this in Richard Furr's app again. By selecting the curve type spline and starting the animation again, we see a more complex graph, which is essentially the point of B-Splines, modeling complex graphs. As we see here, the spline function is made up of pieces, each of which can be represented by a polynomial. In this app, each polynomial is of degree 3. In contrast to the thick red line of the Bezier curve, the spline function contains these little black rectangles, which indicate where to switch from one x of t, y of t pair of polynomials to the next. The parameter values associated with these locations are called knots. We can already see one critical difference to Bezier curves here. At all points, only 4 control points are filled. So again, the yellow circle is always at the center of mass of the 4 blue control points, where the mass of each control point is equal to the area of the blue circle. So, whereas a Bezier curve is always defined in an interval between 0 and 1, a B-spline with the same parameters smoothly transitions from subinterval to subinterval. Although these transitions make it harder to compute, they also allow for much more complex graphs, because we can use more than 4 control points. Let's take a quick look at the formulas again. In comparison to Bezier curves, which are constructed from Bernstein polynomials, and where we have maximally 4 control points, B-splines are constructed with B-spline polynomials, BKD, which limit the control points to D. One important property of the B-spline weighting function is the fact that for every point on the curve their sum equals 1. Thus, every curve point is a weighted average of the control points. If D equals n plus 1 is chosen, the resulting curve is a Bezier curve, which means that Bezier curves are a special case of the B-splines. Alright, we have learned a lot about Bezier curves and B-splines, but seriously, why do we need them in the context of neuroinformatics? While we showed you in the beginning that Bezier curves and B-splines are very useful for image editing, computer graphics and computer-aided design, they can also be used for statistical curve fitting. If you remember the lecture on polynomial regression, curve fitting is the process of constructing a curve that has the best fit to a series of data points. And although we certainly want to avoid overfitting, that is going through each and every data point, including all the noise on the data, it is very helpful to have a tool for modeling more complex curves. After all, the true relationship behind our data is often more complex as well. In the lectures, we looked so far at simple and polynomial regression to model functions for our observed data. And while simple regression only fits a straight line that is constant for the entire possible range of x, polynomial regression can model more complex functions. Nonetheless, these polynomials will fit optimally only when that is the exact nature of the true relationship. Furthermore, polynomials cannot model thresholds and are often undesirably global, meaning that observations at one range of the predictor have a strong influence on what the model does at a different range. But what if there's a relationship between x and y that is different from the possibilities those transformations afford? The answer is B-splines. As we saw, B-splines do not need to be linear and can reproduce pretty much any curve due to their dynamic control points. Moreover, the degrees of freedom are calculated correctly, so you can trust the results, which is not true when you look at your data first and then decide to fit a square term because you saw a bend. In addition, all of this is just another version of the basic linear model. Thus, everything that we get with linear models comes with B-splines as well. For instance, predictions, residuals, confidence bands, tests, etc. etc. Compared to simple or polynomial regression, these are substantial advantages. But of course, there are disadvantages too. The main disadvantage of B-splines is the global influence of the control points on the whole curve, because this means that every change of the control point, insert, move, delete, changes the look of the curve in all points of the curve. And the computational time needed for a big set of control points is comparatively high. Think about it, every time one of the vertices changes, you have to reconstruct the entire curve. So if you have a lot of vertices, and the vertices are changing frequently, B-splines may simply cost too much computing power. To summarize, B-splines are a special case of Bezier curves, which are functions that are modeled by various control points. This achieves a very dynamic modeling, which we can not only use in image editing but also in curve fitting. This allows us to model pretty much any curve we want, which is a big advantage of B-splines as compared to polynomial regression modeling, especially when we have very complex data relationships at hand. The problem is that the control points of B-splines are very expensive with regard to computational power. So, although B-splines are no panacea for the curve fitting problem, they're definitely a very useful tool.